Good morning, everyone. My name is Purnima. I am excited to be here to present an artificial intelligence models for art disease detection using machine learning algorithms, which combines two of the most impactful fields of our time, healthcare and artificial intelligence. I will be discussing how machine learning is being used to predict and diagnose heart disease, a leading cause of death worldwide. Though this presentation, I hope to shed light on how data driven approaches can support early detection, improve patients' outcomes, and assist medical professionals in making informed decisions. Thank you for your attention. Let's get started. Next slide is about the title which follows like abstract keywords, introduction, exploratory data analysis, which is also called as EDA, machine learning models, model evaluation, conclusion, references is about abstract. In this, an heart disease continues to be one of the leading causes of death worldwide. Traditional diagnostic methods can sometimes be time consuming or less accurate, which is where machine learning can make a big impact. So, this research paper explores how machine learning can improve predictive diagnostics via algorithm concentrated on random forest algorithms, a powerful ensemble based method known for its accuracy and stability. So, in our analysis, we only not only used random forest to classify heart disease presence, but also used up various performances matrices and data visualization tools to better understand and interpret the results. So to implement our models we used Python along with the popular data science libraries like pandas for data manipulation, matplotlib and seaborn for visualization, and scikit-learn for building and evaluating machine learning models. So the overall aim was to demonstrate how machine learning can be an effective tool in improving early detection and decision making in healthcare, and which includes the keywords like heart disease detection, Python, machine learning, random forest, logistic regression, data visualization, Google Colab. Next slide is all about introduction. Heart disease is currently the top cause of death worldwide, accounting for over 17 million deaths every year. This makes early and accurate diagnosis incredibly important for efficient treatment and prevention. With a rapid growth of medical data, machine learning offers a powerful and scalable way to analyze patients' information and predict outcomes. Unlike traditional diagnostic methods, which depend heavily on a clinical expertise and costly tools, often unavailable in remote or under resourced areas, machine learning models can work efficiently in consistently. In our research, we used the UCI heart disease dataset to train and test machine learning models using Python. A key aspect of our work is making sure the models produce understandable and visual clear results, especially for medical professionals. This helps ensure transparency in how predictions are made. Overall, the ultimately our goal is to create a practical and expensible systems that supports early detection of heart disease in a reliable way. Next slide is about exploratory data analysis, which is also called as EDA. So, in this slide, we are looking at one of the fundamental steps in exploratory data analysis, histograms. Histograms are used to visualize distribution of different features or variables in data set. As we can see from the plots on the right side of the slide, we have a different histograms representing various features from the data sets. Binary attributes like sex, FBS, which is also called as fasting blood sugar, are heavily skewed. This is expected because binary variables only take the two values like 0 or 1, so which causes the data to cluster around those points. So on the other hand, continuous attributes such as age, CHOL, which is also called as cholesterol, and THALACH, maximum heart rate achieved, show more bell-shaped or spread out distributions, indicating they are more normally distributed. So, understanding this distribution helps us detect data imbalances, identify the outliers. Next slide is about machine learning models. So in this slide, we present a comparison of different machine learning models applied to our data sets along with their respective accuracies. We are evaluated the performances of the following models: logistic regression, random forest classifier, decision tree classifier, k nearest neighbors, which is also called as KNN. So we can study this one by one. Logistic regression, a linear model used for binary classification problems. It gave us the highest accuracy, like 85%, indicating it was the most effective for our data sets. And next one is random forest classifier, an ensemble model that builds multiple decision trees and combines their outputs. This gave 83% of accuracy, showing strong performances and robustness. And next one is decision tree classifier, a simple tree based model that splits the data based on future values. So it gave 80% of accuracy, slightly lower but still reliable. KNN, which is also called as K nearest neighbors, a distance based model that classifies based on the closest data points. It had the lowest accuracy, like 76%, possibly due to sensitivity to data scaling and noise. So, by overall results, we can conclude that logistic regression performed best for our data set, possibly due to the linear relationship between futures and the target variable. Next slide is about model evaluation. In this, the accuracy comparison. Accuracy is a performance metric used to evaluate classification models. It measures how many predictions the model got correct compared to the total number of predictions made. This is the simplest and most direct metric. It shows how many correct predictions were made out of all predictions. The graph likely compares performance matrices of different models for art disease prediction. Understanding how each model behaves helps in selecting the best approach. Here, the x axis represents the machine learning models and the y axis shows accuracy percentage. Each bar represents the accuracy of a particular model. So, the insights from the data are logistic regressions, which achieves the highest accuracy. Random forest decision tree performs well but slightly lower than the logistic regression. KNN has the lowest accuracy, suggesting it may not be best fit for this task. The differences in accuracy shows the impact of model selection on performances. Next slide is about the confusion matrix analysis. So here a confusion matrix is a table that helps evaluate the performance of a classification model by showing how many correct and incorrect predictions is made. It breaks predictions into four categories, that is true positives, which is also called as TP, false negatives, true negatives, which is also called as TN, false positives, which is also called as false positive, false negatives, which is also called as false negative. So, true positive means correctly predicted positive cases. Examples: patients correctly classified as having heart diseases. True negatives means correctly predicted negative cases. Examples: healthy patients correctly classified as decisions free. False positive means incorrectly predicted positive cases. Examples: healthy patients wrongly classified as having heart disease. False negatives, incorrectly predicted negative cases. Examples: skin patients wrongly classified as a diseases free. Here, precision TP plus FB, which measures how many predicted positive cases were actually correct. Recall TP plus FN, which measures how the model identifies actual positive cases. Score precisions into recalls, and precisions plus recall, which balances the precisions and recall accuracy. TP plus TN and TP plus TN plus FP plus FN. Overall, it measures overall correctness. And the key insights from the confusion matrix analysis are: high false positives means the model misclassifies healthy patients as diseased, leading to unnecessary anxiety and tests. I false negative, which means the model misses actual disease cases, which can be dangerous in medical applications. So, balanced precisions and recall. A well performing model ensures it detects diseases effectively without too many false alarms. Next slide is about future importance random forest. In random forest, future importance helps identify which futures contribute the most to model prediction. This is valuable in machine learning, especially for understanding medical data like disease prediction. How future importance work? Random forest consists of multiple decision trees, and each tree makes predictions based on different subsets of the data. The algorithm calculates how much each feature improves model performance by measuring its contribution to reducing impurity. Higher importance means a future strongly influences predictions, while lower importance suggests the future is less impactful. Here, the x-axis represents important scores like 0.00, 0.02, 0.04, 0.06, 0.08, 0.10, 0.12, and 0.14. And the y-axis represents like CP means chest pain type. CA means number of major visuals colored by the fluoroscopy. Thalach, which is mean by maximum heart rate achieved. Old peak means ST depression induced by exercise. Thala means thalassema. So these features have higher importance scores like maximum approximate to 0.10, indicating they contribute most to the model's predictive power. FBS is nothing but fasting blood sugar. Restag is nothing but resting electrocardiographic result. Here, the taller the bar, the more critical the future is for prediction. Taller represent more critical future for the predictions of heart diseases. So next slide is target class distribution. Understanding target class distribution, the target class distribution represents how different categories are distributed in your data sets for heart disease prediction. It helps evaluate whether the data set is balanced or imbalanced, which impacts model performance. How interpret target class distribution in graph? Here the x-axis represents class targets, examples like a heart disease present versus no heart disease. Y-axis represents the number of instance patients for each class. Here the bar height indicates how many data points belongs to the each category. Further slides will be explained by my teammate Saujanya.
Hello everyone, I am Sojana S. I am going to explain about this code. First, we are importing libraries which are required like pandas, numpy, cbarn, etc. Next, we need to upload dataset using this command. df equals to pd.read underscore csv. This is the path of the dataset. Set the visual theme. It is used for white background with grid lines for better readability. It set the default figure size for all floats using matplotlib. Histogram for all features. This code is used for exploratory data analysis. df.hist. It helps you to see distribution of values. Float histogram for each numeric features in the data frame. Figure size make a float large and readable. Edge color. It adds border to each bar and for better clarity. Bins. It break down into a 20 bins. This adds a title for entire figure. Adjust the spacing to prevent a label. It displays the float. Age. We can see here most patients are aged between 50 and 60. Sex. Year 0 is female and 1 is male. We can see male patients more in the dataset. CP, chest pain, from 0 to 3. We can see in the type 0 is the most common. Cholesterol. Peak around 200 to 250. FST, fasting blood sugar. It is common in 120 milligram per dl. 1 equals to 2 true and 0 equals to false. So we can see very few patients have fasting blood sugar. Talach. Maximum heart rate achieved most values around 140 to 170. Slope, CA, targets, etc. So there are 14 features in the dataset. Defines the model's name and their corresponding accuracies. Models include KNN, random forest, decision tree, and logistic regression. Aquarisis 76, 83, 80, and 85. It creates a new figure for the float with width equals to 5 inches and height equals to 7 inches. It creates a virtual bar chart using model names and aquarisis. All bars are colored red. Set the y-axis limits from 25% to 100% for better visualization. Labeling the x-axis equals to models and y-axis equals to accuracy. Set the title for the float. Add the labels on the top of the each bar to show exact accuracy values. Get the height accuracy of the current bar. Plt.text. Place a text label above each bar sh- showing the exact accuracy. HA equals to center. Horizontally centers the text and the bar. VA equals to buttons. Hugging the text at the bottom of the text box. This formula indicates format the accuracy to two decimal places with a percent sign. It rotates the x-axis labels by 45 degree for better readability. It adjusting the layout to prevent label overlap. PLT.show. It displays the float. Model accuracy comparison for art disease. We can see here KNN is 76% and random forest is 83% and decision tree is 80% and logistic regression is 85%. Here we are importing the required libraries. X indicates the all features excluding the target column. Y indicates the target values. It split data into 80% training set and 20% text set. Random state equals to 42 ensures reproducibility of the split. It initializes the random forest with a 100 decision tree. It fits the model to the training data X train and Y train. Uses the trained model to predict the labels for the text data. Confusion matrix creates a matrix comparing actual Y text and predicted Y pred labels. Confusion matrix display a utility to visualize the matrix. It shares the matrix with color blue. It adds the title to the float. It displays the float. Confusion matrix. It shows how many correct and incorrect predictions it made. It breaks down predictions into four categories: 0, 1, 0, 0, 1, 1, 1, 0. 0 means false, 1 means true. It is false positive. 3 healthy patients wrongly classified as having a heart disease. False negative. 1 and 2 sick patients wrongly classified as a disease free. It is a true positive 100 patients correctly classified having heart disease. It is healthy patients wrongly classified having a heart disease. Count float. SNS.count float. It is used to display the count of observation in a categorical variables. Here target. X equals to target. Specifies that the variable target or disease presence should be plotted on the x-axis. Data equals to DF. It tells Seaborn to look for the target columns in the DF. Palette. It sets the color palette for the bar to visualize appealing style. It had title. 0 means a person does not have heart disease. 1 means the person does have heart disease. It labels the x-axis as target and y-axis as count. PLT.show. It displays the float. This code creates a count float. It is a type of bar chart to visualize the distribution of the target variables in a dataset, especially whether the person have heart disease or does not have heart disease. So we can see here 0 means the person does not have heart disease. 1 means the person does have heart disease. So here more than 500 people that does have heart disease. Feature important float. RF feature importance. It accesses the feature importance codes from the trainer random forest model RF. PD.series wraps those important scores into a pandas series assigning x.column. The original feature name as the index. This means each feature name will be associated with its importance score. Sort values. Sort the series by important values from least to most important. It creates a horizontal bar float. It set the figure size to 10 inches wide and 6 inches tall. It displays the title of the float. It labels x-axis as an importance score. It displays the float. Feature important of random forest. We can see here CP is a highest importance. This means the type of CP is a strongly indicator of the heart disease. Say is also a second highest important. This is also an indicator of the heart disease. Sex, rest, ECG, and FBS are least important of a heart disease. SNS dot pair float. It creates a grid of scatter float showing the relationship between each pair of numerical features in the data frame. It colors the data points based on the values in a target column. It gives the title above the entire float grid. It positions the title slightly above the float to prevent the overlap. We can see here the scatter plot graphs. Conclusion. We successfully developed a reproducible, interpretable, and high programming machine learning pipeline for early stage of heart disease prediction using Python. Our approach integrated multiple machine learning model, including logistic regression, random forest, evaluated with robust metrics such as accuracy, conclusion matrix, etc. By combining visual analysis with model evaluation techniques, we enhanced both the transparency and clinical interpretability of the result. An essential consideration for application in healthcare, the use of libraries such as Pandas, Seaborn, Matplotlib, etc. facilitated efficient data handling and visualization throughout the workflow. Demonstrate how AI-driven diagnostic can support medical professionals by providing data-backed insights, ultimately contributing to faster and more accurate disease detection. These are the references. Thank you, everyone.